That's the name of it?
That's the name.
It's harmless.
Allegedly.
That's what you said in the message. Like,
Allegedly, it's, yeah, but the message wouldn't come out until after somebody sent off an email asking if the rumor was true. Okay, questions. Today's topics were basically review, hopefully. There was one newer topic, but do you have any questions off the top of that? So then I guess let's talk a little bit about the idea of having multiple functional groups in the same molecule. And then I'll make up some problems to help us go back and review a little bit more. For Friday, there is a video and the notes for that for the reading assignment on Friday, which is, and I forget off the top of my head what it's I think finishing up, and I may jump ahead a little bit here as well. So we're still in the topic of ethers. So the question would come up about what would happen if I wanted to make an ether out of two primary alcohols. Okay. If the system was set up for like a tertiary alcohol and a primary alcohol, then the first thing that I would need to do to make an ether out of these two alcohols is these two OH groups are both nucleophiles. And so I need an electrophile to make that reaction happen, which means that I would need an H+. Okay. And when you're reacting the H+, in general, the way you're going to react it is you're going to protonate the OH that's going to give you a secondary or tertiary group and then have the water leave to form a carbocation. So, and that might have deja vu back to Monday. So we would protonate the tertiary butyl group first, and then we would go from there. So we protonate the tertiary butyl group to form the oxonium ion. Then that tertiary oxonium ion would lose water, and we would form a tertiary butyl carbocation, which then is perfectly okay to react with a primary alcohol because weak nucleophile plus carbocation, this would overall be an SN1 mechanism because in essence I'm replacing the OH group with an OR group. So then the alcohol would come in, add to the carbocation, and we would end up with the protonated ether, which would then lose an H+ to give us the final, in this case, tertiary butyl ethyl ether would be a common name for that. Because for ethers, you can name them according to the two alkyl groups on either side. So that would be a tertiary butyl group and a tertiary butyl group and a ethyl group. So for a system that has a tertiary or secondary alcohol plus a primary, you're going to protonate preferentially the secondary or tertiary so you can go through the carbocation. But that mechanism cannot occur with two primaries. So let me take away let me make two ethanol molecules, and I'll go through how we would synthesize those two together. So we've used diethyl ether in lab. It's used primarily as an extraction solvent. The nice thing about ethers is that for the most part, since they don't have hydrogen bonding, they have low intermolecular forces, which means they have low boiling points. For the most part, they're water insoluble, and so they make good extraction solvents because they don't react. They make good solvents for things like Grignards because they can't be deprotonated. There are basically only two reactions of ethers, and I'll talk about that. So in this case, I have no choice but to protonate one of the two OHs. So in the industrial synthesis of diethyl ether, what happens is that the first step is to protonate one of the ethanols to form an oxonium ion. But then you cannot have the water leave, or else you end up with a primary carbocation. So in this case, what's going to happen is that my other ethanol molecule is going to act as the nucleophile, and it's going to come in and attack the carbon and kick off the water molecule. So this mechanism is going to be SN2. Now, just because if I asked you this in the future, I might say, let's write the transition state for this, and the transition state for this would have the dotted line between the ethanol and the carbon that is being attacked. So this would be an ethanol CH3 and then the two H's there. So this would be your standard trigonal bipyramidal geometry. The trigonal bipyramidal transition state is what that would be. So if we have that trigonal bipyramidal transition state, then we will have partial bonds. It'll be the nucleophile and the leaving group will be 180 degrees away from each other. The only thing I'm missing here is the charges. So what would the charges be? Not for that. What would the charges be for the two oxygens? Delta plus, both of them? That would be the final product. So delta plus on the oxygens, both oxygens? No? Just the one on the left? So here's my transition state, my standard SN2 transition state of nucleophile carbon leaving group with then my three groups that were attached to carbon. That's our standard SN2 transition state. So I've got two oxygens on in the nucleophile and in the leaving group. So you want the delta plus on which one, left or right?
I changed my mind.
You want both? Do we agree it's both?
Yes.
Anybody not know?
This could be, isn't it oxygen electronegative? I don't know why it's not.
Why it's not partial. Okay. So here's how we calculate the partial charges. Because I'm going to assume that somebody doesn't quite remember this or never knew it to begin with. If you had me, that's not good. So here's how we do the the transition states. So remember, a transition state is going to be an average between the reactant and the product. So the first thing I'm doing is I'm averaging bonds. Oxygen to carbon, there's no bond. Oxygen to carbon, there is a bond. Oxygen to carbon on the OH, on the water molecule, bond, no bond. So that's why the averages are deltas, are dotted lines. Those are partial bonds that are being formed and broken. Now the charges are going to be the average between reactant and product. So if we look at the oxygens, this oxygen right here is 0 or neutral. What is it over here? +1. So what's the average of 0 and +1? Delta plus. So that oxygen is delta plus. And over here, the water molecule, again, same thing. Water, or what becomes the water is plus, 0, average, delta plus. So in this transition state, it is a little bit different than what you've seen in the past because both the nucleophile and the leaving group are sharing in the delta positive charge. So what's really happening is the positive charge is being transferred from the leaving group to the product. So that's why they are both delta positive. And if you go back and look at some of your review problems, some of the transition states I gave you were wrong because they either were missing that delta positive charge or they had a delta negative instead of a delta positive. So that's the way we average out the transition state, is by looking at the charges of reactant product, taking the average. And remember, it's either delta positive or delta negative. Does that make sense to everybody? So then we do a simple SN2. This comes in, kicks the water off. So now I have my oxonium ion. What you would see is this is basically just a protonated ether molecule. So then my bond gets broken between the O and the H, and the pair of electrons goes to the oxygen. I lose my H plus, and so then I end up forming my ether. So the H plus is a catalyst in this case because it's used at the beginning and it's regenerated at the end. So it is not a reactant. It's a catalyst in this particular case. So this is what would happen if both systems were primary and cannot form a carbocation. If one of the alcohols can form a carbocation, then you'll protonate the OH that will lead to the carbocation. And if there was a secondary and tertiary, you could choose the tertiary. If there were two tertiaries, it doesn't matter which one you choose. There's actually multiple mechanisms. If both systems can form a carbocation, you could do one of two mechanisms. So this is what happens when they're both primary, if you want to synthesize the ether that way. And we know that. Because if we go back to last semester in lab, when we did our SN2 reaction to form the butyl bromide out of the butanol, one of the side products could have been a dibutyl ether, and that's the mechanism that you would have written for that. So this is actually the way that diethyl ether is synthesized industrially. Now there is a problem here, and the problem is how do you push the equilibrium? Because a question before the exam was, will we get points taken off if we have the wrong kind of arrows, like an equilibrium arrow versus not. I believe that would be the case probably at the Kent State University, but not necessarily here. But it's my obligation to talk a little bit about, okay, so when are things equilibrium and when are they not equilibrium? And what you're going to see is this diethyl ether could be equilibrium because I could reverse this entire process by basically adding a proton to the ether and then having water come in and attack and kick off the alcohol. So every one of these steps would be equilibrium. And so if you think about some of the mechanisms that you've done in the past, okay, I'm protonating my OH to make my oxonium ion. We've also taken an oxonium ion and lost H plus to make the alcohol. So we've gone in the reverse direction. In this case, I would have to have the water come in and kick off the alcohol, which is possible. So every one of these steps then is reversible. I can lose a proton, or this ether could be protonated. So technically all of these are equilibrium reactions, which basically means that when you take two molecules of ethanol, react it with H plus, it's in equilibrium with the diethyl ether. So how do I push the equilibrium to make only the diethyl ether? And what they do in an industrial situation is they just keep feeding the reactor ethanol. And since acid is a catalyst, they can keep the same sulfuric acid or whatever they're using in the system. Now, don't use HCl, because if we used HCl, what would happen? The Cl would end up making an alkyl halide. So it's got to be H plus from something that doesn't act as a nucleophile as its conjugate base, which is sulfuric acid or phosphoric. So they keep pumping in ethanol, and what they do is they heat this mixture up. Well, ethanol boils like, 78-ish degrees. Diethyl ether boils at like 35-ish. And so what they do is they keep the system heated so that as you form the diethyl ether, it distills out and they collect it. So in essence, what they do is they use Le Chatelier's principle to push the equilibrium and to isolate the diethyl ether. So they can keep feeding it ethanol and keep collecting the diethyl ether, and that's how industrially you can make the diethyl ether. They don't do it like in a big round bottom flask, because a round bottom flask would be like, you'd need a round bottom flask like probably the size of this room. I've only ever heard of one company that ever had a round bottom that big. I didn't see it, but a graduate student came back from an interview one time and said they have a round bottom that's like as big as a room. Everything else is stainless steel. If you don't like stainless steel, it's glass on the inside stainless steel. So that's how you make diethyl ether, and that's how you can make basically kind of any ether. There are other ethers that are used. Diethyl ether we use from ethanol. This would be terse-butyl ethyl ether. Terse-butyl methyl ether is used as an additive to gas. It's called TBME for terse-butyl, and that there's a methyl group on that side. And occasionally it gets loose into the soil, and that is an environmental hazard. So apparently you can use it as an alternative to diethyl ether for extractions, but it has a horrible smell, so we haven't done that yet. But it's less flammable. So that's another way to make diethyl ether. Okay. So that would be the first of our new mechanisms for the next test, which will be the Monday before spring break, I believe. So it's actually not that far in the future. All right, so any questions? So that's how we can make the ethers. So we make ethers by Williamson. We make ethers by using a tertiary halide or secondary halide with an alcohol, because that'll do SN1. And if we need to have two primary systems, we're going to need to do that by SN2. The easiest way is two alcohols with sulfuric acid as a catalyst. Okay. So then it leads to the idea of what are the reactions of ethers. And there's two reactions of ethers that turn out to be kind of important. One of which is you can take an ether and you can react it with oxygen gas and a flame or a spark, and you can do what kind of reaction?
Combustion. Yeah.
So it's going to be a combustion reaction, which means I'm going to make CO2 and water. So the first thing you can do is combust ether. We don't want to do that normally. Although if it's tertiary-butyl methyl ether, if it's this ether, it is added to gasoline as sort of a winter additive to kind of increase your combustion and produce, in essence, less CO2. But for the most part, if we're working in the lab with diethyl ether, we don't want to combust it, right? Which is why we didn't do certain things in lab. We did not take open beakers of ether and heat them directly on the hot plate. That is a recipe for a fire, because the ether vapors are heavier than air. They come out the beaker, they go down to the hot plate, and then if they ignite, then the flames just go right back into the beaker, and then the beaker's on fire. And then you do what a graduate student in my lab did, fellow graduate student, and you knock it over so then the ether rushes across the hood and makes a whoosh sound. And then you look over and you see that the wall is orange from the flames in the lab, or in the hood. And then he yells, "If you know where a fire extinguisher is, please get it." And he had backed himself up, so he was on top of the fire extinguisher. I'm like, move. So then I put it out. The guy from McCall came with this big fire extinguisher, and we put it out. And then we handed the fire extinguisher and said, "Good luck filling out the paperwork on this one." Because what did he not do? That he did claim later on. Didn't use a water bath to heat the ether. That's why you have to use a water bath. And you never heat ethanol or methanol or ether directly on the hot plate because it will catch on fire. But we have to be careful with ether because any kind of spark, and the fumes will be heavier than air. So in our old building that doesn't exist now, we had no hoods. So if we used ether, in the old days, they used to take a tube and make sure the ether fumes were on the floor where there was less likely to be a fire. But you could have the fumes go across the bench top and ignite way down there. So you have to be careful using diethyl ether because it will combust very easily. So that's one reaction. For the most part, ethers are unreactive, but they will combust very nicely if you give them a chance. Number two is they form peroxides. So if you took diethyl ether and it sits around in oxygen gas for a long period of time. So in other words, where this would be a problem is if you had really, really old glass bottles of diethyl ether in the lab, and they did not have an antioxidant in them to stop this process, they will form peroxides. So oxygen in its diradical form is a diradical. Okay? And so it can undergo a free radical reaction. So the free radical reaction that oxygen can undergo is it likes to abstract hydrogens from carbons or from other oxygens, from alcohols, and form stable or unstable radicals. So what happens is that if ether sits exposed to oxygen for a long period of time, what will happen is we will end up with arrows that look like this. So these are the fishhook arrows that indicate movement of one electron. So this O dot comes over and pairs up with the H dot that results if I split this bond with one electron to each atom. So the H dot pairs up with the O dot to form a OH group. And the carbon then ends up as a radical with an unpaired electron. And that unpaired electron is sitting next to the oxygens. So if you, in your mass spec, when we did mass spec in lab, you could think about, well, here's a radical next to an oxygen. There's probably some resonance structures I could draw here by maybe moving this over here, putting the oxygen as a radical, or maybe even sort of trying to form a double bond of some sort. So that carbon then forms the radical. Now, what happens is that the other end of the peroxide, or what's going to become a peroxide, now the other end of the oxygen molecule just pairs up, couples with that C dot. So one end of the oxygen gas pulls the hydrogen off, and then the other end adds to that carbon radical so that we end up with the OOH on the ether. And this is called a peroxide. Hydrogen peroxide is HOOH. Whenever you have organic alkyl groups on either side, it's called an organic peroxide. So this would be an ether peroxide. This process will occur over time. So I haven't heard of this being an issue for quite a while, but when I was a graduate student, I remember the guys coming in with their space suits or explosion-proof suits and carrying glass bottles of ether that have been stored in somebody's lab for a long period of time out to the bomb disposal truck, and hoping they didn't detonate along the way, although I think they put them in one of those big steel containers where they detonate stuff. But they had their spacesuits on just in case. And so they were walking across the parking lot and were like, I hope that wasn't my lab that they found that in. Because the problem is with glass bottles, you would have the peroxides form very readily. Now, what's the problem with this peroxide? In general, if you would like to make something that is a good bomb candidate, you embed a gas molecule inside of a solid, so that way when you heat it or shock it, like pick it up, then that can be converted to oxygen gas. And so whenever you have a solid that becomes a gas, there's a huge expansion, and that's what makes a good bomb or explosive. It's a basic theory on making a good explosive, is embed a gas molecule in your molecule. So with peroxides, what would happen is you would end up with white solid at the bottom of your ether. And then you would just walk out of the room and carefully close the door and not touch it, and get somebody to come and take care of it. The last thing you wanted to do was to turn the screw, turn the cap, because if there were peroxides in there, that's shocking the system. And if you do that, you always do it with the hand you don't write with, in case you are sans that hand at the end of the experience. But that used to be a huge issue. It's not so much now, because when we get ether, we usually get those old silver bullet cans that we get them in. They have sort of a coating. They also add an antioxidant to this. And the antioxidant that's normally added is the same kind of antioxidant that would be in food, which is typically a phenol. So if you add some sort of phenol to this, and a phenol is a benzene ring attached directly to the OH. If you add that as an antioxidant, they do add this to food all the time, because the same free radical reactions that you can have with ether, you can have with food, and that's why it spoils. Besides bacteria and mold and all of that stuff, what happens is when you remove that H and you form a dot there, there's all sorts of resonance structures you can draw. And the best thing to do to kill radicals is you can't really kill them. Best thing is put them together, couple them. But if you want to get rid of oxygen as its radical form, turn it into a very stable radical, which is what the phenol becomes. So then it doesn't propagate. The other issue is when you're doing free radical reactions, what happens? One radical generates another, and it just continues down the line. So in this case, they add a little bit of that antioxidant to it, and that's added to all sorts of things. If you look at some essential oils have that antioxidant in it. Perfumes sometimes have that antioxidant because the components of the oil can undergo these same kinds of reactions. But with ethers, the issue is that if you see an ether bottle and you see white solid on the inside of it, you just walk away quickly as possible. I did get a phone call from a former student who is now a superintendent of a school district, which is scary. They always mature when they leave here. But he was teaching at, I believe, Riverside High School years ago, so none of you, if you went to that school, would know him. But he called and said, we have a isopropyl ether bottle in our lab that's really old. And my advice was, walk away and call somebody. Because this whole process intensifies if that's a secondary radical. Because the secondary radical is even better to form. It's more stable. So that's just peroxide waiting to happen. And then he said his colleague went in and unscrewed the cap. And I said, does he still have both of his hands? And he's like, yeah. And I said, well, tell him he's lucky. Because that will form peroxide. So there's really only two reactions of ethers. Well, there's three. These are two. Peroxide formation, bad. Combustion, in lab, bad as well. So ethers, for the most part, don't react, but when they do, they form, in this case, really bad things. So that was another topic that, if you heard it in the video, it's this. I probably did exactly the same thing, but those are our two reactions. So this mechanism of peroxide formation is just another free radical mechanism that we've, similar to free radical halogenation, but just a twist on it. Then I think the other topic for today was silyl ethers. So, and I think there was a video on that, but what is the point of silyl ethers and why won't you go forward? So we, so far, have just been doing reactions with one functional group in the molecule. That's it. Right? I mean, that's not real life. Real life is when I'm doing reactions, I've got multiple functional groups in the molecule, and what I have to do is I have to make sure that if I'm trying to react this functional group, that the other functional group doesn't react as well. All right, what am I talking about? Could be something like this. No, something like this. Let's say I would like to convert that molecule to that one. My first question would be, could you tell me what reagent would add two OHs to a double bond? Cis hydroxylation.
KMNO4 and OH minus.
KMNO4 and OH minus. Is there another one?
OSO4 in each ocean.
OSO4, osmium tetroxide, and hydrogen peroxide. Now, osmium tetroxide, hydrogen peroxide would probably not touch the OH group, the alcohol that's already there. But let's just say it's too expensive and I can't afford it. But I can afford KMNO4 all day long. So I want to do this reaction with KMNO4. And I would use base, but I'm still using KMNO4. What's the problem? What's the problem in doing that reaction? Will it convert the double bond to two OHs? Absolutely, that's why we chose it. Will it react with the existing OH group? Will KMNO4 react with a secondary alcohol? And what will it form? A ketone. So I will not get this molecule. I will get that molecule. Okay, but I could get from there to here if I did what? What am I changing in this molecule? I'm changing the ketone to a secondary alcohol. Okay. In general, when you have these kinds of problems where you're trying to figure out the reagent, if you're stuck, what's changing? The carbonyl is becoming an alcohol. What kind of reaction is that? SN1? Am I substituting anything? No. SN2? I'm not substituting anything. Am I forming a double bond? Not elimination. Acid base? No. No acid base. So what's left? Oxidation reduction. Okay. So what could it be? SN1, it could be an SN, could be an E, could be a deprotonation acid base. It's not a Grignard or anything like that. It's a reduction. Reducing agents. So if you think about this and you go, okay, I'm turning carbonyl into an alcohol, that's reduction. What are my reducing reagents? Two possibilities.
Is it the LiAl?
Lithium aluminum hydride or sodium borohydride. So I could reduce that ketone into a secondary alcohol by using either one of those. So is it possible for me to do that transformation of adding two OHs to the double bond? Yes, but in this case it takes two steps. Is there another way around this? And the answer is yes. If I do something called protection. So we're going to talk about protection later on, but if I protect the OH group and keep it from reacting, then I can do whatever I want to the double bond. So I'm going to do basically a protection reaction. So I'm going to take that alcohol and I'm going to protect it by reacting it with what's called, this would be called trimethylsilyl-chloride. And there are other of these reactions, but this is the best. This is the one that the book introduces. So what I'm going to do, the terminology here is I'm going to protect that alcohol so it doesn't react. And so what happens when we react an OH with a chlorine that's attached to silicon? the same thing that happens when we reacted an OH with a chlorine that was attached to sulfur. I'm going to lose HCl. And I'm going to basically make an OSI with the 3 methyl groups. And so I'm going to replace the OH bond with an O silicon bond. This is called a silyl ether. Okay. And once you have a silyl ether, it's going to be stable to most reagents except one. Okay? So you make this silyl ether, it will not react with KMNO4, for instance. So now I can say, okay, let's go ahead and react this with KMNO4 and base and put my 2 OH groups where the double bond was, but my oxygen still stays as a silyl ether. Nothing happens to the silyl ether. So now I can do my reaction on the other parts of the molecule, and my OH group is protected against that. So this would be a protected alcohol, is what it would be called. Okay, so I've got my protected alcohol and as a silyl ether. So I do my reaction on whatever else I want to do, but now I need to get rid of the silicon at the end. So I need to de-protect. And so this O silicon bond is stable to everything but one reagent. And the one reagent is fluoride. So if you react this now with fluoride, what will happen is that we will basically remove the silicon and we will go back to the alcohol. And the reason for this is because the silicon-fluorine bond is one of the strongest ones that's out there. So if you want to de-protect a silyl ether, you just dump in a little fluoride. It's going to be fluoride and water. And then what will happen is that the silicon will come off. And so this would be what we would call our de-protection step. So this is the first of a couple of different protection, deprotection schemes that we'll talk about. And this is getting us to really what most organic synthesis people do. I mean, if you want to make a drug, you're going to have to deal with multiple functional groups. And if you don't want one, if you're going to try and react one functional group but leave the other one intact, you're either going to have to find a reagent that's very specific for one of the two reagents or one of the two groups, or you protect the other one. But in order to protect it, you got to get it back at the end. So silyl ethers are one of the examples of a protection-deprotection scheme to be able to do that.
Do you also have to add like H+?
Yeah, so the fluoride is going to be an aqueous solution. And it would be probably, I would use maybe cesium fluoride for this. There's a potassium fluoride, there's probably sodium fluoride, but you would use, I think most synthetic people would use a cesium fluoride. So it's already in the water to get the OH back. But the binding of the silicon and fluorine, that bond is so strong, that's what removes the silicon. So other than that, that silicon's going to stay intact. And so synthetically, that's a way to protect alcohols. And there's other ways to do it as well, as esters. And you might say, well, you know, how often do people do this? And I'll just show you, here is a structure that you most likely have seen in the past in another class. You've seen molecules that look like that when they're written flat. When they're written like this, right? What is that?
Glucose or some sugar.
It's a sugar. I don't know if it's exactly glucose or not, but it's a six-membered cyclic sugar. So there's two ways to use sugars. Back in the 70s and 80s, there was a thought that if we run out of oil, which at that point there was the Arab oil crisis and all sorts of things, that it was like, do we have an alternative to make our plastics and everything else if we run out of oil? And so there was a thought, well, we can grow sugar all day long, or somebody can grow sugar all day long. Can we turn those sugar molecules into everyday materials? And you can, right? Plants do this. They turn this into starch, right? So that's one way. But the other way is, if I want a drug to go into a cell, there has to be something to take it across the cell wall, right? Because normally it's just a door and it doesn't open up, right? You got to be invited in. The best way to invite the drug molecule in is to put sugar on it, and then it'll pass through the cell wall maybe a little bit easier. But then you got to actually put your drug molecule on one of those OH, but they all look the same. So what you end up doing is having to protect some and leave the one you want open to then do the reaction with, and then deprotect all the others. So people that do sugar chemistry end up spending more of their time protecting OHs and deprotecting OHs than they actually do doing the productive reactions, because they have to be very specific about the OH group they want to put their drug molecule on. And so we'll talk about this later on, because if the two OHs in the ring are cis, I can protect those, whereas if they're trans, I can leave those two open. So that's another place where people want to protect OH groups. They don't normally do it with silicon, but you could if you wanted to. So the idea here is this is kind of our initial very, very tiny amount of toe dipping in the water to say what would happen if we had multiple functional groups in the molecule. We would have to think about doing a reaction but not reacting the other. So that's what the silyl ethers, their purpose is, and that's how we would do that, is with the trimethyl silyl chloride and then fluoride. Okay, so we'll have a quiz on Wednesday over these reactions. I'll send out an email on that. And the video for Wednesday is up, and lecture materials. Also, if you're behind on your Chapter 13 and Chapter 14 top hat, I will record the grades on those probably starting on Saturday morning, so Friday would be a good time to get those done by.
Dr. Nichols, I have a really random question. In my other class, it's like a gender studies linked course, but they said that they used to use ethers to make women forget about labor and childbirth.
Well, ethers were originally used as your anesthetics for surgery.
Is that anything like? They wanted to know if it's anything like chloroform.
Yeah.
Okay.
Except ethers were first used in surgery. So I mean, if you breathe in too much ether, you can pass out.
That's not bad.
But I mean, they're not used now, right?
Yeah, right.
Because for them to be used now, you would run the risk of